This time I'll be talking about unsupervised and semi-supervised learning of structure with neural networks. And so to talk about, before I talk about unsupervised or semi-supervised learning of structure, I first want to kind of define supervised, unsupervised, semi-supervised. And most of the models that we've handled so far in this class are based on supervised learning. And basically, supervised learning is where we have a model of P of y given x, and at training time, we're given both. And sometimes we are interested in unsupervised learning, where we want to model P of y given x, but at training time, we're given only x. So we want to have a model that induces something useful from basically thin air, from nothing, nothing whatsoever. Or in semi-supervised learning, we want to model P of y given x, and at training time, we're given either both or only x. And usually we're given both for a small portion of data or only x for a larger portion of data. And I think this is an interesting thing to think about a little bit more carefully now, especially given that unsupervised and semi-supervised learning are now, fundamental to all NLP learning problems. And it's very hard to build a state-of-the-art system without using some sort of unsupervised learning somewhere. So to give a little quiz, and if you want to answer yes or no here, I see before I even asked, somebody said yes, so I guess you want to answer the question. When we are learning, when we're training BERT, are we doing unsupervised learning? So I've gotten some split opinions on this, and I think that's fair because this is a kind of hard question. So when we're training BERT, if you think about what we are learning, what is our goal of learning? What do we want from the BERT training objective? And I think the answer is we don't actually want like a good language model, or at least in most cases, our goal is not to learn a good model for predicting masked out words in a sentence. That itself has also proven useful in some cases. But basically, in BERT, the supervised learning problem is there is a supervised learning problem, and the supervised learning problem is basically like if we have a sentence with a masked out word, can we predict that word? So in that case, the sentence with the masked out word would be X, and the word, the masked out word itself would be Y. And can this model be used for anything? Or can this supervised learning problem be used for anything? And the answer is yes. A model trained in the supervised fashion can be useful for something. And some examples of things that can be useful are performing question answering. So if you want to do, if you want to answer the question, let's see if I can find a good example. The capital of the capital of Japan is, and then you do blank. BERT is a supervised training algorithm, and it has been trained to solve exactly this problem of filling in the blank, and it could answer Tokyo, right? So that's one use of BERT to solve the supervised learning problem, where it has a supervised learning problem of filling in the blanks, and then you could apply it to exactly that problem. Um, so yes, BERT is performing supervised learning, but at the same time, it's also performing a form of unsupervised learning. So what is it learning there? It's learning the latent features of the language, or it's learning a feature extractor for the language. And that's actually the majority of the uses of BERT, of course. So, the way we would use BERT normally is we take the BERT pre-trained model, and we take the features that were learned from the model and we apply them to some downstream task, either by freezing the features and using them as is, or fine-tuning the model. So in that sense, the BERT objective is an unsupervised objective. And what is it learning unsupervised? It's learning features that are useful and generalizable downstream. So it is a tricky question. And the good news is if you answered yes, you're correct. And if you answered no, you're also kind of correct, because it's performing supervised learning of a word predictor, but it's also performing unsupervised learning of features, or at least that's my interpretation. So are there any questions about this? Okay. So I will move on to the next slide. So um, as I said, BERT or other kind of embedding models are learning features. And there's a distinction between learning features and learning discrete structure. And the features could be something like word or sentence embeddings, like exactly what I just talked about. But another thing that we could learn is discrete structure, and that would be something like, taking in text and getting a tree that represents the syntactic structure of the text. So why would we want to learn this discrete structure in the first place? And I think there's two major motivations behind this. The first major motivation is, for example, if we want to use a model that models information flow within a neural network different ways depending on the structure. So this would be, for example, the tree structured composition models that I've talked about before, or some sort of model that does passing between co-referent objects within a sentence or something like this. And these methods have proven useful, at least in some cases, for improving the performance. Another reason why you might want to do this is if you want to actually get out some sort of interpretable structure. And this would be used mostly for showing it to humans, who could then use that structure to perform analysis or better understanding of the underlying text. So just to very briefly review unsupervised feature learning, when we're learning embeddings, we have an objective and use intermediate states of this objective. So for example, SIBO and skipgram are things that either predict the context given, the central word given the context, or the context given a central word. We could also have sentence level autoencoders, skip thought vectors, variational autoencoders. So these are just any of the many examples that we have here. And all of these are basically word prediction or sentence prediction objectives. But we don't actually use them as word predictors or sentence predictors, but we rather use the features that were learned in an unsupervised fashion in a downstream task. And specifically, how do we use them? We can use them to solve tasks directly. So, we could perform some sort of manipulation over these features, like taking the vectors between them and use them to predict analogies, for example. And by proxy, do things like knowledge-based completion, et cetera, which we'll be covering in a few classes. But mostly these have been used to initialize downstream models. Oh, yeah, and to solve tasks directly, yeah. So knowledge-based completion is just one example, and there's, of course, many other things that you could do as well. So what about discrete structures? So one example of something that we could do from like simple word vectors is we could cluster words together. And what that would say is, oh, we can look at the clustered words and say, oh, these two words might be similar, and show that to a human. And say, do you want a synonym of this word? And if so, here's a good example. Another thing we can do is we can cluster words in context. So for example, this could be something like unsupervised part of speech tagging, where we take words in context and we try to cluster them so that the clusters correspond to some syntactic function of the word. Or we could do it for something like named entity recognition, where we try to cluster together entity spans in coherent ways. Or we could learn structure. And one example of the structure would be something like the tree structure that I just talked about before. So in doing so, what objective do we use? And in general, unsupervised learning will have some sort of generative model of the data X. And this is also more or less true for things like BERT, of course. They're being trained to predict the data X. And in learning how to predict the data X, they also learn some of the underlying structure of the data as represented by features. In our case, we sometimes, like in the case of inducing latent structure, discrete structure as opposed to continuous features, we can sometimes factorize this in this way. So we have a prior over the underlying structure Y, and then we generate the output X given the structure Y. And this is kind of a generative model in the traditional sense. And we could also factorize it, basically predict Y given X, and then predict X given Y. So this would be an autoencoder. And this can be made mathematically correct. And like as Trenting presented last week, we can do this through a variational autoencoder where, we actually have a prior Y, but we are using an inference network to help us learn the model kind of more effectively or efficiently. So are there any questions so far on this part? Okay, that I will move forward. So next, I'd like to talk about repeat the part about the inference model. So if you look at the traditional generative model here, we have a prior over our latent structure Y, and then we calculate the probability of X given our latent structure Y. We could also have an autoencoder that basically predicts Y given X and then regenerates X given Y. The variational autoencoder, which we talked about in the previous class, is very similar to an autoencoder from the point of view of model structure. So we have an inference network that takes an X and predicts Y. And then given this predicted Y, we regenerate X. However, from the point of view of the math of the model that it's actually learning, it's closer to this traditional generative model where we have P of Y and where we have P of Y and then generate X given Y. And the reason why we're able to do this is because we have the KL divergence term between P of Y and Q of Y given X. Yeah, and we talked about this in a fair amount of detail last time. So if it's not clear, we can you can go back and review that. Okay, so now moving to clustering words in context. So a simple first attempt to cluster words in context. We could train word embeddings or contextualize word embeddings and perform k-means clustering on them. Or well, we could train word embeddings and then perform k-means clustering on them. This is actually implemented in Word2Vec. So they have the classes option there. So this was something that people were thinking about from the very beginning of learning word embeddings. And however, the problem with this is if we want single words to appear in different classes, in other words, if we want the same surface form, but different values of the surface form, but different classes depending on the context, then this obviously won't work. So another thing we can do, I'm sorry, I don't actually have any slides about this, but another option in order to do this is to train contextualized word embeddings, like BERT or whatever other ones you like, and perform k-means clustering on them as well. And this will give you words in context. But the problem is contextualized word embeddings express a whole lot of different things. So they express semantics and syntax, etc. And it is not super easy to disentangle these different problems. These different features of the contextualized word embeddings. So instead, we can turn to more like carefully formulated generative models that allow us to learn exactly the type of clusters that we would like to know about. So one example is if we want to learn syntactic structure for like underlying syntactic structure of the words in a sentence. And a way we can do so is through hidden Markov models. And the hidden Markov model is a factored model of P of X given Y times P of Y. And so in other words, it has a prior over Y and then generates X given Y. And this is done through state-to-state transition probabilities and state-to-word emission probabilities. So specifically, the state-to-state transition probabilities are basically like the probability of going from the beginning of the sentence to an adjective, and then the probability of going from an adjective to a noun, probability of going from a noun to a noun, etc. And then our emission probabilities basically generate a word given the part of speech tags. So generate natural, given that it was an adjective, generate language, given that it was a noun, etc. And I think a lot of people are familiar with this. It's also very similar to the CRFs that we talked about before, in that it is doing this local factorization where you only calculate the probability of the only calculate the probability of the tags given the immediately neighboring tag. So this model in itself, you see we have the part of speech tags here already. And if these part of speech tags are annotated, then learning this model is relatively easy. All we have to do is we have count up the part of speech tags and divide. So we count the number of times we've seen an adjective, and then we count the number of times we've seen a noun given an adjective. The previous word was an adjective, and then we divide the latter quantity by the former quantity, which gives us this, transition probability from adjective to noun. But what if we wanted to learn this in an unsupervised way? So to learn it in an unsupervised way, basically what we do is we change the labeled states to unlabeled numbers. So essentially we have a number representing each underlying state here um, that we don't necessarily know which part of speech tag that this would apply to. And in order to learn this, basically what we do is we initialize the transition probabilities and the emission probabilities semi-randomly. And then we can run the forward-backward algorithm, just like we talked about, in the previous class on CRFs, to try to maximize the probability of the output given the label sequence. So just in case people haven't remembered the CRF class, what we did in the CRF classes was we basically ran a dynamic programming algorithm from the previous state to the next state to the final state, and we calculated the marginal probability over all paths and then optimized the parameters in order to increase that marginal probability. And we can do the exact same thing for a hidden Markov model. Now, count-based hidden Markov models are one way to kind of induce structure, or like kind of syntactic categories for words. One of the reasons why these work well, or perhaps work better than just clustering BERT embeddings or something like that, is because actually this independence assumption between the tags allows you to learn kind of more localized information. And syntax, the great majority of it tends to be local. So what do I mean by this? Basically, if you look at the left word and you see the left word as an adjective, you look at the right word and you see the right word as a noun, the middle word is very, very likely to be a noun. And a great majority of the time, you are able to learn this information without actually looking at the whole sentence or something like that. So the independence assumptions that the hidden Markov model makes is actually well tailored to this test. And this is a very important theme in all of kind of unsupervised learning of structure, which is that you need to carefully design your model so that the inductive bias of the model matches the type of thing that you want to learn. So in this case, it's syntax. So we match the inductive bias to try to match syntax. To give a counterexample, so let's say it wasn't syntax that we wanted to learn, but rather the topic of each word. So in that case, there are topic models, and what topic models do is they completely ignore local word order and just look at the co-occurrence of words in a document. And because of that, the document topic tends to be coherent across the document. You can completely ignore this word order and just use essentially a bag of words of the document, and this will give you a better concept of topics. So that's another example of an inductive bias that you can use to try to induce the latent structure that you want. Are there any questions about this? Okay, I don't see any, so I will move on. So the hidden Markov models, they've been around for a long time. The traditional way to do this was, as I mentioned, just calculating these probabilities based on counts. But unfortunately, this has problems, just like all of the count-based language models that we've talked about at the beginning of the class. And so what a next step that we can do is we can start taking this count-based model and move it into neural land. or at least continuous representation land. And the way we do so is instead of parameterizing each state of the hidden Markov model with a categorical distribution, we instead use a Gaussian distribution over word embedding space. Sorry, we instead use a Gaussian distribution. So basically what that means is class number 13 has a Gaussian, class number 17 has a different Gaussian, class number 6 has a different Gaussian, etc. And for a long time, these models were kind of the de facto standard in speech recognition. But they were also applied to part of speech tagging by essentially training a Gaussian unsupervised part of speech tagging by training the Gaussian to emit word embeddings. So you have a Gaussian over word embedding space, and you use this to just induce the hidden states. And so this is, taking our really simple baseline of trying to induce something like part of speech tags by clustering word embeddings, but instead also making it context sensitive by having these transition probabilities in the hidden Markov model. So yeah, and actually I already talked about this. This is like, this is essentially BERT, like what I talked about by clustering the BERT outputs. But actually the idea of doing this is much, much older. It went back to Giles et al. 1992. And so what they did was they trained an RNN according to a standard loss function, such as a language model. And then they clustered the hidden states according to k-means, et cetera. So this is another option you could do, but empirically this doesn't, for part of speech, unsupervised part of speech induction anyway, this doesn't work as well as the more sophisticated methods using hidden Markov models for the reasons I already mentioned. So there are more, so the hidden Markov model that emits, that has a Gaussian over the word embedding space is an interesting and simple method. But it also makes some very strong independence assumptions. So it makes independence assumptions about the part of the transition distribution, and says the transition distribution is consistently the same across all sentences. It also makes independence assumptions, or the assumption that a Gaussian is a good model of the hidden word embedding space. So instead, what Tran et al. 2016 do is they calculate the transition and emission probabilities directly with a neural network. And for the emission probability, they calculate the representation of each word in the vocabulary with a CNN. So basically, instead of just using a word embedding, they calculate the representation with a CNN directly. And then they take the dot product of the tag representation and do a softmax to calculate the emission probability. For the transition matrix, they calculate the transition matrix by running an LSTM over the sentence. This unfortunately breaks the Markov assumption, but nonetheless, they find this improves accuracy a slight bit. So they see that by running an LSTM and using that to directly calculate the transition probability between words, this improves the accuracy. So the first part here, basically this allows them to directly take into account like the spelling of words, for example. And the second part allows you to relax the independence assumption a little bit. So another issue, if you're using something like pre-trained word embeddings, is that the embeddings themselves may not be entirely indicative of the syntax that you want to learn. So to give an example, this is from a paper by Junchen here at CMU. And he, well, and I'm a co-author on the paper, but he visualized the word embeddings by running dimensionality reduction over them, and then colored the each point in the space according to its part of speech tag. And what you can see is essentially that this, there is some separation. So you can see that the orange parts representing proper nouns tend to be clustered together. The yellow parts representing verb base forms tend to be clustered together, etc. But there's also quite a bit of mixing between the different parts. So for example, you see the light blue and the light purple, which are plural nouns and singular nouns, tend to be clustered together. So if you're going to do something like, so given this, having a simple Gaussian might not be an expressive enough distribution to model this. So the method he proposed was instead to learn part of speech taggers with latent embeddings. So in other words, we have our standard hidden Markov model. So this is our Markov structure, just the tag sequence. And then we have a latent embedding space, where the latent embedding space is a space that can be modeled well using a Gaussian for each each class. But then in addition to this, we have a neural projector that goes from this latent embedding space and induces a distribution over the actual observed embedding space. So it's a two-step generative model like this, or I guess 3 steps. So we first generate the underlying part of speech sequence. We estimate the latent embedding, or a calculated distribution over the latent embedding, and then we generate the real embedding from this, or the distribution over the real embedding from this. So yeah, sorry, I'm gonna skip this. So in order to do this distribution mapping, we use a method called normalizing flow. And basically the idea behind normalizing flow is it's a way to map from one probability distribution to another in an invertible manner. And so in other words, we have our latent underlying distribution, and then we have a neural projector that that maps from the underlying distribution to the space here, and then from the space that I see, I have a question. Let me get to that in a second. And then on the other hand, we have a method that kind of inverse of this mapping function that goes from the more complicated distribution to the less complicated distribution. So I had a question, which is reminding what the purpose objective of these methods are. So just to go back, the goal of these methods is basically to learn discrete clustering of words in context. And the idea of like one example of learning a discrete clustering of words in context would be learning part of speech tags. And part of speech tags are useful because, like, let's say you want to do linguistic analysis of a language, like in perhaps an unknown language. You could run this this method over the text of the language and learn the underlying syntactic categories of each of the words that you have there. And that could be useful for, for example, a linguist trying to understand the language or something like that. Another example of clustering words in context would be clustering words by topic. So that's what we do in topic models. And topic models are useful if you want to analyze the topics of documents, or if you want to know, what topics certain words tend to be used in. So like if you have a word that you're not familiar with, you could figure out how it was used in different contexts and find examples of that. So either way, basically what you want to do is you want to go from a word in the sentence context and map it to a cluster that represents something you are familiar with, or that is understandable to a human. Does that kind of answer the question, or was it? Okay, thanks. So, and just to recap here, one way you could do this is by leveraging word embeddings, by taking this generative model and having it emit not the words itself, but the word embeddings. But the problem with that is that the word embeddings actually conflate a lot of different things and might not be necessarily clustered well according to whatever property you're interested in. The one example being syntax. And so because of that, we want to map into a different space where the word embeddings indeed are clustered well according to the feature that we're interested in, namely, in this case, syntax. So basically, we have a distribution in kind of our latent space that is easily clusterable. And we also have a neural projector, this phi, that takes the latent embedding and maps it into the actual observed embedding. And then we have the observed embedding, and are also able to map it back into the latent embedding using the inverse function of this original projection. And so the kind of ingenious or very, very interesting thing about this method called normalizing flow is that if you can have this sort of mapping function, and if you can calculate the determinant of the Jacobian matrix, so the Jacobian matrix is basically the derivatives of all the inputs and outputs with respect to each other. You can then train this efficiently. By doing a fair amount of math, you can demonstrate that the log determinant of the Jacobian plus the probability of the model in this latent space after mapping through this projection function is equivalent to optimizing the probability of X in the original space. So I'm not going to go through all the math here, but it's basically a neat trick if you have some sort of latent distribution that's relatively simple, and then a more complicated distribution that you want to model that isn't quite as simple. And so, in this case, we used it specifically for mapping from the latent Gaussian to the more complicated distribution over observed data. Another example, just to kind of put this in a different perspective, is you could also do a similar thing, something similar to like a variational autoencoder, where the latent distribution is a latent distribution over your hidden variable z, and the more complicated distribution is the distribution over like natural images or something like this. So you have your latent distribution here, and you can map to a generative distribution over something much more complicated. But anyway, that's the high level idea. And when we're learning in this case, what we found was after you performed the learning with the hidden Markov model and you ran this model with a latent embedding, if you visualize the latent embeddings, you can see that they're much better clustered according to the actual part of speech tags, which is kind of what we would like. We'd like them to be clustered such that they can be modeled with a simple Gaussian. And we also found that the performance by doing this in this way was quite a bit higher as well. Okay. Sorry, I understand that this is very high level, but are there any quick questions with respect to this? Okay. If not, I want to point out one interesting potential application of unsupervised methods. And it has, so one argument that you could make against unsupervised methods is, for most language tasks that we care about, we have supervised data in English. So, why do we care about unsupervised structure induction in the first place? We already have data in English, and one way of applying models to languages that don't have lots of data is to just train a big multilingual BERT model and apply the model that we learned in English to the new languages. And if the underlying representations learned by a multilingual BERT model are good enough, then it should be able to transfer quite well. And we're going to talk about details of this, but basically from an engineering perspective, this is quite effective and often more effective than completely unsupervised methods. However, in this paper, also by Jane Chen, we demonstrate that unsupervised learning actually does have some advantages. And basically what we did was we pre-trained generative models in a supervised fashion on a high resource language. So we took our hidden Markov model or our, or a more complicated syntax based model. We trained it supervised on English. So in other words, we gave it the classes corresponding to actual part of speech tags and, trained it by counting up and dividing. But then we fine-tuned the generative model to improve the likelihood on a low resource language. So this doesn't require any sort of, like annotated data in that particular language. And we demonstrate that this significantly improves accuracy over the more kind of naive method of training a big unsupervised representation learning, multilingual representation learning model and just applying it to the new language. And it's particularly true when you're transferring to distant languages. And basically what this shows is when the language is very different than the original language that you're trying to transfer the model from, this kind of unsupervised fine-tuning allows you to discover the structure of the language by learning over lots of data, and in order to just maximize the probability of the data. So in this way, kind of unsupervised models can also be used for semi-supervised learning by optimizing the likelihood on data that you don't have labels for. Another notable result from this paper is the results were not as good on similar languages. And the reason why is because the generative models that I presented here are less strong than powerful discriminative models that we can train on English when we have fully supervised data. But in a way, I think this is perhaps an exciting result, because what this shows is there are very clear advantages to having generative models that can be trained in an unsupervised way. So maybe we, more work could be done on training better unsupervised models. Better generative models, which can be trained unsupervised. Okay. Are there any questions? Okay, I'll continue. So next, I'm going to talk a little bit about unsupervised phrase-structured composition functions. And so we talked a little bit before about tree-structured composition functions. I think we talked about this when we talked about parsing several classes ago. And they're in the context of those, composition functions, we talked about hard tree structures, where it's basically like we take the left child and the right child, we run them through an LSTM, and we use the corresponding vectors as the representation of a phrase. However, there's also methods that use soft tree structure, which essentially use some sort of differentiable gating function to try to represent the underlying tree structure. A hard composition function would look something like this, and a soft composition function would not have a single tree structure that we're using, but would rather have okay, we believe this tree structure is likely with 80% accuracy, and this tree structure is likely with 20% probability. So before I go into specific methods for learning kind of this soft composition functions, one other paradigm, in addition to supervised or semi-supervised or unsupervised learning, is weak supervision. And basically, weak supervision in supervised learning, we're given X and Y to model P of Y given X. Unsupervised, we're given X to model P of Y given X. And weakly supervised learning, we're given X and V to model P of Y given X, under the assumption that Y and V are somehow correlated. And this is different from simple multitask or transfer learning, because in multitask learning, we have some data of P of V given X, we have some data of P of Y given X, and we learn both of the models jointly. In this case, rather, we are given no Ys, so basically Y is completely unsupervised, but we do have some information about V, which is another thing that we think is, related to Y. It's also different from supervised learning with latent variables, because we care inherently about the latent variables rather than the output of the output V. So a first example of soft tree structure actually goes to Cho et al. 2014, and this uses a method called gated convolution. Interestingly, this gated convolution later evolved into GRUs, which we've already talked about. But the way the gated convolution worked is essentially you had a convolution operation, but the convolution operation could choose to either use the left child in a binary tree, the right child in a binary tree, or use the combination of both as calculated by a gating function. So I got a question. Should it be P of V given X? This is under the weakly supervised case. So actually, no. This is the slides are correct, and this is kind of important. So we're given x and v, and we would like to learn a model that can predict the probability of y. So to give an example, um, let's say, well, okay, the best example of this is the semantic parsing case that we talked about, uh, or one example of this would be the semantic parsing case that we talked about earlier. So in the semantic parsing case, one example of this would be um, we want to learn a method that goes from natural language commands to programs. And the learning signal is provided given pairs of natural language programs and input-output examples. So in this case, X would be a program. Sorry, X would be the natural language. Y would be a program. And V would be the input-output examples. So um, the reason why input-output examples are good supervision for programs is a correct program will get the input-output examples all correct. An incorrect program will get the and an an incorrect program would often get the input-output examples incorrect. So we want to learn a model that goes from natural language to programs. And we actually care about the programs. So because of this, why our programs are the things that we actually care about. But we can use the input-output examples to help distinguish between bad programs and good programs. So the model we're learning is P of y given x, but we're using something else, V, namely input-output examples, to learn that P of y given x. Does that make it a little bit more clear, or? So V is like an intermediate. V is actually not so much intermediate. V is Y would be more like a latent state. So let me see if I can draw this here. So we have everyone can see the whiteboard, right? Yes, I see yeses. So we have this model here. We have the model that goes from X to Y. And at training time, we have V. And in some way, we can use V to validate Y. So Y could be, for example, a program, and V could be input-output examples. X could be a natural language command. So the latent state is actually this, or the latent variable is actually this Y. But we can use V to kind of validate it or correlate with it or something like this. Maybe another good way to think about this is think about it a little bit like a reinforcement learning problem, where our goal is to go from X to Y, where Y is a set of action sequences, and V is used to calculate a reward over Y. That would be another way to think of it. It doesn't encompass all of weakly supervised learning, but it's one example. Does that make a little bit more sense? Okay, great. So I will go back to the slides. So gated convolution is one example of a way to induce tree structure, because basically the left side, depending on the gating function, you can kind of see a latent underlying tree structure. So this example, Obama is the president of the United States. Um, you can see that most of the time it's combining together information from multiple sources. But once you get up to here, um, you're just passing Obama all the way up to the very top um, without you know without any modification. So you can see the information flow within the model. Um, so this was trained. There were no annotated gates, no annotated gating functions. Rather, this was trained using a machine translation loss function. So this is an example of weak supervision because in this case, the V would be a translated sentence. And the Y would be this kind of tree structure that you could visualize to learn more about the structure of the sentence. Another way to learn this is to learn using reinforcement learning. So in this case, this gated convolution is an example of a soft tree structure. If you want to learn a hard tree structure, you could, for example, learn it using reinforcement learning. So it uses an intermediate tree structured representation for language modeling, and it predicts that tree using shift-reduce parsing, which we've already talked about here. And the sentence representation is composed in a tree-structured manner. And the reinforcement learning, so the way the reinforcement learning works is basically how well do you do at predicting the next word in the sentence given this tree structured composition function. And this is an interesting technique. The only problem with this is it actually doesn't work or didn't work super well. And there's kind of a common theme of learning latent structures for language in neural networks, where these kind of reinforcement learning approaches tend to converge to kind of boring, uninteresting solutions, like this solution on these two solutions on the very right, where you either have a left branching tree or a right branching tree that just doesn't learn any useful intermediate structure. And part of the reason why is if you have a parser, essentially a shift-reduced parser, that's getting its feedback from a language model, the language model has to learn to use that useful structure. So there's kind of a chicken and egg problem where at the very beginning of training, the parser doesn't work well, so the language model can't learn to use useful structure. And the language model doesn't work well, so the parser can't learn from the language model. So these methods, while kind of interesting and promising, definitely have their issues in learning actual useful structures. So in general, these kind of soft tree structured methods tend to work a bit better. And one example that was particularly useful or particularly successful was this method by Choi et al. And the way it works is basically they have a softmax at each layer that decides which two words to combine into a phrase. And so in this case, you have a softmax over each of the possible combinations. And in this case, it will, the cat has the highest probability, so it will combine the and cat into a single phrase. This was trained using the Gumbel straight-through reparameterization trick, which was similar to the Gumbel softmax, which we were talking about last time. And it proved faster and more effective than learning using reinforcement learning. However, there are still, underlying difficulties in learning latent structure. Um, as I just said, unfortunately, many models still learn trivial structure, such as balanced binary trees, left-to-right branching, etc. So this is one example of a balanced binary tree that these models can learn. Um, and like, as I said before, there's a tension between the untrained parser and the untrained downstream task model. And this is just a problem that's quite difficult to overcome. Um, so are there any questions on that part? Okay, I guess not, so we'll move forward. So I'm going to very briefly talk about learning dependencies. So as we talked about before, phrase structure versus dependency parser versus dependency structure. Previous methods attempt to learn representations of phrases in a tree structured manner, but we might also want to learn dependencies that tell us which words depend on others. So for phrase structure, okay, so for learning parts of speech, we talked about hidden Markov models. So hidden Markov models are kind of a dynamic programming based approach to find all the paths through a sequence and assign them latent states. We've also in the past talked about the CKY algorithm in parsing, which is a dynamic programming approach to calculating tree structures, which can also be used for tree structure induction. The equivalent for dependency parsing is something called or one equivalent for dependency parsing is something called the dependency model with valence. And the basic idea is that it's a top-down dependency-based language model that generates the root of the sentence first. Then it generates the left and right children of each word in the tree, and then it stops. So if we have this example, I saw a girl with a telescope. For both the right and left side, it calculates whether to continue generating words, and if yes, it generates a word. So to give a slightly simplified view for the word saw, it would first say, given that the word is saw, the direction is left, and we haven't generated a word before, we want to continue. And because we continued, we generate the word I. And then on the left side, our word is saw, our direction is left. We have already generated a word, so we stop generation. Then saw on the right, we generate girl. Saw on the right, we generate with, and then we finish. Sorry, that should be a right pointing arrow, not a left pointing arrow. So that's a typo. So this is, and there's a dynamic program that can calculate this, the marginal probability of this model. So we can train it in a very similar way to how we train HMMs or context-free grammars. And of course, people have applied neural networks to this as well. So the simple way is to parameterize each decision with neural networks instead of count-based distributions. And like the dependency model with valence, we can train the model using the EM algorithm. So essentially, it's just a neural parameterization of the standard dependency model with valence. And Junshun in his work, where we also did the hidden Markov models, he had a similar formulation for the dependency model with valence, where instead of using a hidden Markov model to calculate this, this structure up here, we apply it to the dependency model of valence. Basically, the neural projection part that I talked about previously is exactly the same. It's just that we changed the underlying dynamic program to induce this structure. And another thing we can do is we can take a model um, and look at its attention distribution to try to induce which words are kind of the head of a phrase. So in this work here, we given a phrase structure tree, we determine what child is the head word or the most important word of the phrase. So the idea is to create a phrase structure composition function that uses attention. Like we've talked about different phrase structure composition functions, like the tree LSTM, or doing a bidirectional LSTM over all of the words in the phrase. The key idea here is that instead of doing the LSTM or either of those, we instead have an attention-based function and then look at the attention values for all of the words in the phrase. And if you look at the attention values and take the maximum one, you can see that kind of sometimes it corresponds to what we would expect to be the head of the phrase. So for example, company here is the head of the phrase and it gets the highest value. Real assets seem to be kind of important and they get the highest value, etc. So finally, I'm going to go through a few other examples. So one other example is learning how to segment words. So word segmentation is something we don't think about a whole lot in English because English, we write the language with spaces and it tends to be morphologically poor, so we don't have to worry very much about having lots of complicated conjugations or things like this. But in other languages that have richer morphology, or even more interestingly, perhaps, speech data doesn't have any underlying segment boundaries. So you need to kind of discover them. So this method here basically learns how to do word segmentation by training a machine translation model that translates from one language to another, and then looks at the attention matrices and tries to turn these attention matrices into segmentation over the words. And the red boxes are essentially the true alignments within here, and we can see that the attention essentially corresponds to this as well. So this is another example of being able to use attention to kind of induce some sort of underlying linguistic structure. Another example is this paper on learning segmentations with reconstruction loss. So basically, the goal here is to learn segmentations of speech or text that allow for easy reconstruction of the original signal. And the idea is that a consistent segmentation should result in easier to reconstruct segments. And this is trained using policy gradients. So to give an example, we have down here we have the underlying phoneme sequence or character sequence or whatever. And the proposal is basically, okay, we're going to segment here, we're going to segment here, and we're going to segment here. And based on this, we segment, we encode each of these strings, and then we try to reconstruct the segment based on this reduced latent representation here. And the idea being that if we learn segmentations that correspond to real words, this reconstruction objective will be easier, and we'll be able to compress the information down better. But if we learn segmentations that are incoherent, it will be a lot harder to do so. Um, Another example of some sort of interpretable structure that you can learn is learning language level features. So this is an example of some work that we did here at CMU. And most of the previous works that we talked about learned features on a single sentence or perhaps a, you know, at the very most, a document or something like this. But this paper that we presented here tries to learn features of the whole language. So for example, typological features like what is the word order? Is it a subject, object, verb language, a subject, verb, object language, etc. And in order to do so, we did a simple method where we trained a neural MT system on a whole bunch of different languages. We extracted its representations, and then we use these to predict the features of the whole language. So this is the unsupervised learning part. In this case, is kind of the feature learning part. So it's not actually really unsupervised learning of latent structure, but we demonstrate that these unsupervised features can then be used to predict, you know, features of the whole language. So I guess that is all I have for today. I think these methods are kind of interesting, especially if you're more linguistically oriented and want to discover you know, things that we didn't know about language in an interpretable way that can then be used to analyze the language or learn more about it. So if that's kind of your something you're interested in, I definitely encourage you to take a closer look at these methods. Are there any questions that I could answer before we finish up? Okay, I'm not seeing any, so I guess I will see you next Tuesday, and good luck with the assignment, everyone. See you later.